Let's work through example 8 to find the Maclaurin series for sine of x. This is a very important Maclaurin series, and we want to see how to develop it. Maclaurin series is just a Taylor series centered at 0. Our function is sine of x. The general form for a Maclaurin series is the sum from 0 to infinity of the nth derivative evaluated at 0 times x to the n all over n factorial. The only thing we have to figure out here is the nth derivative at 0. So we're going to create a table, take derivatives, look at plugging in 0. For this example, we want to take a bunch of rows so that we can see a pattern emerging here. So we take the original function, f of x, which is just sine. Now take the first derivative of sine. The derivative of sine, that's cosine. Take the second derivative. Derivative of cosine is negative sine. Take another derivative. Derivative of negative sine is negative cosine. Take another derivative. The derivative of negative cosine is negative sine. Positive sine. Look at this. We're back to where we started. The fourth derivative of sine is back to sine. So what's the next derivative? Well, it's just going to be cosine, and then negative sine, and then negative cosine. We're going to keep cycling through these different values for the derivative. So the fifth derivative, that's cosine. Sixth, negative sine. Seventh derivative, negative cosine. Eighth derivative, we're back to positive sine of x. We're taking all of these derivative values and we're plugging in 0 for x to get this next column here. So we're going to look at sine of 0. Sine of 0 is 0. Next, cosine of 0, that's the first derivative at 0. Cosine of 0 is 1. Negative sine of 0, that's 0. Negative cosine of 0, negative 1. And now we have the same pattern repeating. So 0, 1, 0, negative 1. That keeps on repeating because we have this cyclic nature of the derivatives of the sine function. So sine of 0, 0. Cosine of 0, 1. Negative sine of 0, 0. Negative 1, 0. It keeps on going. For this example, rather than trying to predict a formula for the nth derivative at 0, it's actually a little more useful to just expand out the first several terms of the Maclaurin series using these values for the nth derivative. So we're just going to expand this out. When n equals 0, we have the 0th derivative at 0, that's just the function at 0, 0 times x to the 0 over 0 factorial. When n equals 1, then we plug in 1 for the nth derivative at 0, so we'd have 1 times x to the first over 1 factorial. So 1 times x to the first over 1 factorial. When n equals 2, the nth derivative at 2 is 0, so we'd have a term of 0 x squared divided by 2 factorial. That term just goes away. So we go to the next term. If we plug in negative 1 for the third derivative, we'd have negative 1 times x cubed divided by 3 factorial. The fourth term, the degree 4 term, we just plug in 0 for the fourth derivative at 0, so we get 0. So we skip over to the degree 5, n equals 5. If n equals 5, then the nth derivative at 5 is 1. So we have plus 1 x to the fifth over 5 factorial. Now look at the pattern that we've got going on here. Every even term is gone. This 0 times x to the 0 over 0 factorial, we could get rid of that. And we just have odd powers of x. We have x to the first over 1 factorial, x cubed over 3 factorial, x to the fifth over 5 factorial. And they're switching signs. We have positive, negative, positive. The next one would be negative x to the 7 over 7 factorial. The pattern continues. Can we write this in shorthand sigma notation? This is the expansion of the Maclaurin series, but let's write it down in shorthand. We have the sum. N goes from 0 to infinity, and we only want odd powers of x, and we have that same power factorial in the denominator. The way to get odd is to do 2n plus 1. So I'm going to write x to the 2n plus 1. If n equals 0, we have 2 times 0 plus 1, 1. If n equals 1, we have 2 times 1 plus 1, 3. So using 2n plus 1, I get 1, 3, 5, 7. I have the same expression in the denominator's factorial. 2n plus 1 factorial. There's one other thing going on here. There's this plus minus behavior. How do we get the alternating sign, S-I-G-N? we multiply by -1 to the n. And now we have to check. Do we have plus minus plus minus, or do we have minus plus minus plus? Well, if we plug in n equals 0, we'd have -1 to an even power, that's positive. So when n equals 0, we have positive for the first term. That's just what we want. So this is correct, -1 to the n. Here is the Maclaurin series for sine of x. This is a very important series. We want to be really comfortable with this particular Maclaurin series. Now we're going to graph this in Desmos and see if we can guess the radius of convergence for this Maclaurin series. Here's our graph of sine of x, and I went ahead and typed in the Maclaurin series that we just found. Let's take more and more terms of the Maclaurin series, and we'll watch how the series, well actually it's a polynomial if we have a finite number of terms, we'll watch how the polynomial starts to look more and more like the function sine of x. We want to know what is the radius of convergence. So focusing around 0, we want to know how far on either side of 0 does the Maclaurin series start to look like the function sine of x. So let's take more and more terms and see what happens. Isn't that cool? As we take more and more terms for the Maclaurin polynomial, it starts to match up better and better with sine of x, and it just keeps going. If we zoomed out here, we could see that it just keeps matching up more and more. The radius of convergence here is infinity. If we take, say, the first 50 terms, let's see how far it converges for that. Taking more and more terms, we get better and better convergence further and further away from 0. The Maclaurin series goes off to infinity. So as m goes to infinity, as we take more and more terms, we get a power series that converges to sine of x exactly. The radius of convergence here is infinity. This Maclaurin series exactly equals sine of x for all values of x. Now that we've found the Maclaurin series for sine from example 8, let's take a look at example 9. We are going to find the Maclaurin series for cosine, and we're not going to just do it from scratch like we did for sine. Instead, we will take the Maclaurin series for sine and take the derivative of the series to find the appropriate Maclaurin series for cosine. This is actually an important concept that we'll see in future videos. We can take a known Maclaurin series and do something to it to get the Maclaurin series for a related function. Let's see how this works. Here's our Maclaurin series for sine. We know that that converges to sine of x for all values of x. And now I want to find the Maclaurin series for cosine for example 9. And we know that cosine is the derivative of sine. Well, we just saw that this is the Maclaurin series for sine. So instead of taking the derivative of sine, we can take the derivative with respect to x of this Maclaurin series. Now I know there's a lot going on here, but remember this is just like an infinite polynomial. So we're going to take the derivative of this power series with respect to x. So we'll just replace sine of x with the power series here and then talk about how to take the derivative. We have the derivative of the summation, where n goes from 0 to infinity, of -1 to the n, x to the 2n plus 1, divided by 2n plus 1 factorial. How do we take this derivative? How do we compute this thing? Well, we're taking the derivative of a sum. And when we take the derivative of a sum, we can just independently take the derivatives of the independent terms and then sum them all up. This is the same as saying if I take the derivative of a function f of x plus a function g of x, I can independently take the derivatives of f and g. This is the same as f prime plus g prime. I'm just independently taking derivatives and then adding the results. This works if I'm adding. It doesn't work for multiplying. That's why we have the product rule. But here, the sigma notation is just addition. So if I'm taking the derivative of a sum, that's equal to the sum of the derivative. So in essence, I can actually switch the sum and the derivative notation. So we have the sum, from n goes from 0 to infinity, of the derivative of all this stuff inside. -1 to the n, x to the 2n plus 1, divided by 2n plus 1 factorial. So the derivative of a sum is the sum of the derivatives. Now how can we take the derivative of this expression here? -1 to the n and 2n plus 1 factorial, those are constants with respect to x. So we can bring those constants out front of the derivative. Let's do that. So we have the summation notation outside, and then we're taking this constant, -1 to the n divided by 2n plus 1, and removing that in front of the derivative. -1 to the n divided by 2n plus 1 factorial. And now we have the derivative of what is left. We just have x to the 2n plus 1 left. So the derivative of x to the 2n plus 1. What is the derivative of x to the 2n plus 1? This is simply the power rule. I take the power 2n plus 1, bring it out front, and subtract 1 from the power. So I can now evaluate this derivative here. I'm going to copy down the summation notation still. -1 to the n divided by 2n plus 1 factorial times 2n plus 1 times x to the 2n. I'm going to do one step to simplify this just a little bit further, and then we'll have the Maclaurin series for cosine. 2n plus 1 factorial, well, let's just write this off to the side. 2n plus 1 factorial is all the numbers starting at 1 times 2 times 3, multiplying them all together until we get to 2n plus 1. 1 times 2 times 3. We keep going. The last number that we'd multiply here is 2n plus 1. And right before 2n plus 1, we have the preceding number, 2n. And right before that, we'd have 2n minus 1. So I'm just thinking of expanding out the 2n plus 1 factorial. Notice that right here, 1 times 2 times 3, all up until 2n, this is just 2n factorial. So I can write 2n plus 1 factorial. If I just group these factors together, inside those parentheses, it's just 2n factorial because I stop at 2n. So I can rewrite 2n plus 1 factorial as 2n factorial times 2n plus 1. So in the summation notation here, I'm going to replace the 2n plus 1 factorial with this equivalent expression. I have the sum, again from 0 to infinity, -1 to the n. 2n plus 1 factorial I write now as 2n factorial times 2n plus 1. And in the numerator, I have 2n plus 1 times x to the 2n. So these can cancel. And I have finally the Maclaurin series for cosine. It's the sum, n goes from 0 to infinity, -1 to the n, x to the 2n divided by 2n factorial. We found this without having to create that table like we did for sine. And look at the similarity between the Maclaurin series for cosine and the Maclaurin series for sine. The Maclaurin series for sine has odd exponents on the variable and then odd factorials. For cosine, we have even exponents and even factorials. We have a very similar Maclaurin series for sine versus cosine. This is a very powerful idea, that we can find a Maclaurin series for some function if we know the Maclaurin series for a related function. We'll see this more for some future examples. Finally, let's solve example 10. For example 10, we want to find the Maclaurin series for the function f of x equals 1 plus x to the k. Here, k can be any real number. Let's see what we get. Our function is f of x equals 1 plus x raised to the k. And we are finding the Maclaurin series, or the Taylor series centered at 0. So let's write down that form. The Maclaurin series is the sum from 0 to infinity of the nth derivative of the function evaluated at 0 times x to the n divided by n factorial. We're going to set up our table, and we're going to try to come up with an expression for the nth derivative of this function evaluated at 0. In the first row, we just have the original function f of x, 1 plus x to the k. And then if we plug in 0 for x, we have 1 plus 0 to the k. So f of 0 is simply 1. Now take the first derivative. How do we take the derivative of this? Well, we have something raised to a constant power. So we take the power up front and reduce the power by 1. So the first derivative here is k times 1 plus x to the k minus 1 power. Let's look at the second derivative. We're going to do power rule again. The k minus 1 pops out front. So we'll have k times k minus 1 times 1 plus x to the k minus 2 power. Take another derivative. K times k minus 1 times k minus 2 times 1 plus x to the k minus 3 power. Do you see the pattern? Each time we're multiplying by 1 less from the power than what we had in the expression before. Now let's plug in x equals 0 into each of these expressions. If we plug in 0, notice that we'll have a 1 raised to some power. 1 plus 0, we have 1 raised to some power for each of these different expressions here. So we're just going to have the coefficients that are sitting out front. So f prime of 0, that's just k. F double prime evaluated at 0 is k times k minus 1. The third derivative evaluated at 0, k times k minus 1 times k minus 2. Let's use these values now to look at the expanded form for this Maclaurin series. We're going to start when n equals 0, and when n equals 0, we first have the nth derivative at 0, the 0th derivative at 0, which is just this, just the function at 0. So we'd have 1 times x to the 0 over 0 factorial. X to the 0 is 1, 0 factorial is 1. This is just times 1, so we don't even need to write that. Now let's look at the n equals 1 term. When n equals 1, we take the first derivative evaluated at 0, that's k. We're going to write k times x to the first over 1 factorial, which is just k times x. Now we take the second derivative evaluated at 0. This is the n equals 2 term. So we'll have k times k minus 1 times x squared over 2 factorial. Now the n equals 3 term. We have the third derivative evaluated at 0, k times k minus 1 times k minus 2 times x cubed divided by 3 factorial, and the pattern continues. So here's the expanded form for this Maclaurin series. We'd like to get a more compact form. What we want is an expression for the nth derivative evaluated at 0, so we don't have to write the whole thing expanded out like this. We'll look at our table, and we'll try to write down an expression for the nth derivative at 0. When n equals 1, notice that we just have k. When n equals 2, we have k times k minus 1. n equals 3, k times k minus 1 times k minus 2. What will we get in general with n? We're going to get k times k minus 1 times k minus 2, and this is going to stop. Notice that it always stops at 1 less than n. K times k minus 1, which is 1 less than 2. K times k minus 1 times k minus 2. 2 is 1 less than 3. So this will stop at k minus n minus 1. I stop here at 1 less than n. Look again at the pattern. I stop this expression at 1 less than 2. I stop this one at 1 less than 3. So I'm going to stop this one at 1 less than n. That's what I get in this pattern. So this is the nth derivative evaluated at 0. Let's plug that into the Maclaurin series. We have the summation, n goes from 0 to infinity, of the nth derivative at 0. That's k times k minus 1 times k minus 2, all the way up until k minus n minus 1, divided by n factorial times x to the n. This shorthand form is a little bit better, but it's still kind of bulky because we have this expression here where we've got a whole bunch of stuff multiplied together. So we're going to give this fraction its own special notation. We're going to call this fraction right here k over n. And we read this as k choose n. This is called a binomial coefficient, and the series that we're creating here is called the binomial series. Binomial, bi means 2, nomial number, and we have 2 numbers, so that's where the name binomial series comes from. This expression is associated with binomial series, so it's called a binomial coefficient. Binomial coefficients are used in all sorts of area of mathematics. We're not going to get very in-depth with binomial coefficients here, but this expression here, we're going to define to be this piece of notation. In parentheses, we have k over n. It almost looks like a fraction maybe, but there's no bar here for a fraction, and it doesn't mean fraction. By definition, we're going to choose this notation to mean exactly this expression here. There's another problem with this expression. Not only is this kind of long and bulky, but it doesn't work when n equals 0. If we plug in n equals 0, we don't get something that's meaningful here. So we're just going to choose that k over 0, by definition, we're going to choose to be 1. So we'll just write down here, k choose 0, by definition, we'll define that to be 1. So we can write our binomial series in a simpler form as just the sum n goes from 0 to infinity, k choose n times x to the n. Once again, we are defining this piece of notation, this k over n. It's read as k choose n. So k choose n. We are defining this to be this fraction right here involving the factorials and this expanded product. Once again, this is called the binomial series, and it's the Maclaurin series for the function 1 plus x to the k. For our purposes, this is really all you need to know about these things called binomial coefficients and the binomial series, but it's very possible that you'll see these sorts of numbers again in future math classes.